I finished my first degree in the mid-'80s, and I knew at that point I wanted to be a group theorist. So I asked my tutor where I should go to do group theory, and he said, oh, well, I was at Oxford at the time, but he said you should swap to the other place because that's where they're doing all this amazing group theory. And so he sent me up to Cambridge, and he said I should go and talk to this guy here, John Conway. So I went and had a meeting with John about, it was 1985, I think. And John was very proud because he just received the sort of first copy of the Atlas, and he very proudly slammed this thing down in front of us on the desk. He said, well, if you want to join our group, we're very obsessed with symmetry here in Cambridge. So he said, so what's your name? I said, Marcus do Sautoy. He said, well, I'm afraid you're going to have to drop the do. Because all the authors in his group all had 6 letters in their name. So I thought, maybe he had something against French aristocracy. But no. So I said, okay, I've lost my chateau in France already because of the revolution. So I'll drop the do. He says, okay, but have you got some initials? I said, yeah, MPF. He says, yeah, well, you're going to have to drop one of those as well because we only have 2 initials in our name. So I thought, okay, MP Sautoy. That's fine. He said, no, there's one more condition on here. So John had the first idea of putting together all of this amazing work over 150 years to put all the finite simple groups together in this thing they called the Atlas, which was growing. They weren't quite sure whether it was going to be infinite. Rob Curtis, his student, joined and helped him on the beginning of this journey. And then there was this rather annoying guy who just hung around the office all the time, but he actually turned out to be quite good at navigating all of these finite simple groups. His name was Simon Norton, and so they said, yeah, he could join the group as well. Then Parker as well, he was a wizard at the computing that was needed to complete the project, and then Wilson was the last one to join. So they all joined in alphabetical order. John said if I was going to join them in Cambridge, I would have to change my name to MP Sautoy in order to... At that point, I thought, this is a little bit too much. And so I went back to Oxford and decided I'll try and do some group theory in Oxford. But I was a little bit worried at this point because, I was only an undergraduate looking for my some research to do. And I thought maybe actually group theory had been finished. Here we got this kind of the Atlas, the periodic table of symmetry, and maybe there was nothing left to do. But that turned out, of course, mathematics is a bit like a Greek hydra. You finish one problem, 2 more appear. So I went back to Oxford, and I started going to some lectures by Dan Siegel, who turned out to be my DPhil supervisor. We call our doctorates DPhils rather peculiarly in Oxford. And Dan had just finished his project with Fritz Grunewald and his first PhD student, Jeff Smith, or to finish, I think that's always the... and they'd just started looking at the idea of actually trying to classify. Classification is a very important part of our subject, but they were looking to try and classify not finite simple groups that had been finished, but actually a class of infinite groups, nilpotent groups. And they introduced this idea of a tool which they thought would perhaps give you some way to get some hold on this classification of something like infinite nilpotent groups. And it was a tool that came from number theory, Zeta functions, which are the topic, the title of my talk. So the Zeta functions, so here's Dan's here, Jeff's still in England, and it's very sad that Fritz isn't here. I think Fritz would have loved this conference, and it's very sad that he died far too early. But they introduced this idea of the Zeta function, which is a kind of generalization of the Zeta function from of a number field. The idea is instead of taking a lattice of ideals inside a number field, maybe there will be some interesting invariants to help you to classify infinite groups by looking at an analytic object which somehow took the lattice of subgroups of an infinite group and tried to encode those in some sort of Zeta function. So they introduced the idea of counting the number of subgroups in this, the lattice of subgroups inside an infinite group. So if you take a finitely generated group, then you could count all of its subgroups, or you could just concentrate something on like its ideals, the normal subgroups. So we define A sub n of G to be the number of subgroups of index n in G, and if it's finitely generated, this is a finite number. and the normal subgroups as well. And so there's been a lot of study done here in Jerusalem as well as in Oxford and elsewhere on looking at the rate of growth of this and what it tells you about the group. But there's more subtle ways you can understand these invariants, which is to encode them inside a zeta function. So you take a Dirichlet series, and the coefficient of the Dirichlet series is given by this counting function. And then you can ask, so the rate of growth of this will be related to the abscissa of convergence of these functions, but you can ask whether this is giving you interesting invariants which might help you to classify classes of, say, nilpotent groups. And the paper that Grunewald, Siegel and Smith wrote was looking at the class of nilpotent groups, and they made the first sort of calculations of these groups. And you can see it's a sort of generalization of these Dedekind zeta function of a number field, a sort of non-commutative version now of this. The most simple example is the infinite cyclic group, which only has one subgroup of each given index. So when you encode this, you just recover the Riemann zeta function. Slightly more interesting example, so Jeff Smith was responsible for some of the very early calculations. If you take the free abelian group, you get a product of zeta functions, Riemann zeta functions. But perhaps the first interesting example which Jeff calculated was to take a nilpotent group of class 2, so dimension 3, Hirsch length 3, so the upper triangular matrices over Z, and if you calculate the zeta function of this piece, then you again get a result which is in terms of Riemann zeta functions, but slightly more sort of subtle things going on here. And Grunewald, Siegel and Smith proved in this paper that actually, if you look at a local zeta function, so just count the subgroups of p-power index inside the group. If the group's nilpotent, then you know that the finite nilpotent group decomposes as a product of its C-loft P subgroups, and that actually translates into a nice Euler product. So actually the global zeta function pulls apart into just being built out of the subgroups of p-power index inside the group. So you have a nice way to actually analyze the global zeta function as just a product of these local factors. And what they proved, and a very beautiful general result in that paper, using some very interesting techniques of model theory, p-adic integration, resolution of singularities, they proved that this zeta function is always a rational function in p to the minus s, which is a pretty impressive result. And it shows that the number of subgroups essentially satisfies a recurrence relation. So there's a very controlled pattern inside here with these coefficients. So a rational function means that these coefficients, there's some recurrence relation connecting the coefficients. So I was given this paper. I was a bit shocked actually because it was full of integrals, and I'd actually tried to, I said, but I'm a group theorist. Why am I doing integration? I tried to leave that behind. I was rubbish at integration. So, but this is a different sort of integration, p-adic integration, and it's much easier integration actually. All the mistakes you make in analysis as a first year undergraduate all are right in p-adic analysis. So it's great. It was the analysis for me. So I was interested in generalizing, well, how much further can you go with this sort of result? And the thesis that I wrote under Dan's supervision was to prove that if you take a p-adic analytic group, so a finite extension of a pro-p group, and as Alex proved that the pro-p groups, and Avinorm, that pro-p groups where these coefficients grow polynomially will have a p-adic analytic structure, and this you can use to actually build up these integrals and prove that in general a p-adic analytic group will have a rational zeta function counting its lattice of subgroups of prime power index. And this is about as good as it gets, because if this is rational, then these things grow polynomially, and so any pro-p group must have a p-adic analytic structure on it. So it's about as good as it gets. It's interesting, the first sort of calculations, so actually my first PhD student, when I was working in Cambridge, and Ishai Alani, who's here as well, we started to explore, for example, well, what if you take a small p-adic analytic group which isn't nilpotent? So we actually calculated the first example. So if you take, say, SL2 ZP, that's a finite p-adic analytic group, then actually, or take its congruence, first congruent subgroup, which will be a pro-p group, then actually you can calculate the zeta function, and again you get these local zeta functions coming out with a slight extra term for the prime p equals 2. So this also has a sort of decomposition in terms of a sort of pro-p. Well, this should be actually pro-finite completion maybe here. But I always set my PhD students, when they start with me, the sort of challenge of extending this, because there really has been no progress over the last couple of decades in calculating any zeta functions of p-adic analytic groups beyond SL2. I mean, it's crazy. We know so much about SL3, SL4, SLN. We don't know anything about these zeta functions in generality across, say, a class like SLNZ, what their abscissa convergence is, what their behavior is. So, and it seems like a nice open problem to explore. We know they're rational functions, but what's the behavior of these rational functions? How does it relate to the structure of these algebraic groups, these p-adic Lie groups? So it was about this time I finished here, and I'd spent a lot of time reading papers about p-adic analytic groups, and I kept on reading these papers by this one guy who seemed to be just talking the same language as I was. There weren't many people in the sort of 90s who were doing p-adic analytic groups, but this guy Alex Lobotsky kept on coming up, and I realized, I had to go and find out who this guy was, because he clearly was understanding p-adic analytic groups as well. So I'll perhaps talk a little bit later in the dinner about our first meeting in Norman, Oklahoma. But Alex invited me to Israel. I mean, I think there are many of us here who've benefited from the invitations we've had. I came to the Institute for Advanced Study, where there was a program going on field arithmetic. I joined that, and Alex and I worked on looking at these rational functions. In particular, we were quite interested. So this was one of the papers. I mean, Avinoam had actually come to Oxford, so I'd met him. So, but I was quite keen to come and work with Alex. So here's Alex. I think this is at Oberwolfach, shortly before Fritz died, actually. So, so I was quite interested in a question, actually, that was posed in that first initial paper by Grunewald, Siegel, and Smith, because if you've got a nilpotent group and you've got all of these rational functions in p to the minus s, there's an interesting question. If they're all rational, what's the connection between these? Are they actually all the same sort of shape, or do they vary? So you vary the prime p. And there was a very interesting example that they'd calculated where they'd taken the Heisenberg group, but not put the integers in, but put a quadratic extension of Q. So they put the ring of integers inside this group. So this is now a group of Hirsch length 6. And what was interesting is that the rational functions varied according to how the prime p behaved in this number field. You've got just different structure of subgroups and different counting properties. And interestingly, actually, if you piece these together, you can express the global zeta function in terms of the zeta function of the underlying number field, which kind of hinted at maybe there was some sort of Chebotarev density type theorem, which was explaining the behavior as you varied the prime. And they raised it as a question because they weren't going to elevate it to a conjecture because it was very little evidence really at that point. But they said, yeah, maybe if you take a fixed finitely generated nilpotent group, we know that all the zeta functions are rational, but maybe there are actually only finitely many rational functions in two variables, x and y, which actually capture the whole range of local zeta functions. So for each prime p, you'll pick one of these, and you'll substitute p for x, which will give you the coefficients, and y will be p to the minus s, and so there'll be a finite division of the rational functions into types, perhaps depending on the way a prime behaves in a number field associated with each finitely generated nilpotent group. And they actually were able to prove this. We'll call the group finitely uniform if it has this behavior. So they were able to prove for class 2 free nilpotent groups, and actually extending that example of the Heisenberg group, if you put the number field in, sure enough, the prime behavior of the prime in that number field is determining how the rational functions vary. So we'll call that finitely uniform if this behavior is true. Now, actually, Alex and I, when I was here, we started working on a variant of these zeta functions, which is counting. I said you could count subgroups. You can also count normal subgroups. But we looked at a variant which counted subgroups which were isomorphic to the original group. And these can actually be described by integrals over the algebraic group of that nilpotent group. So we actually were looking at zeta functions associated to the algebraic automorphism group of these nilpotent groups. And we proved a uniformity result which really depended on the way the prime behaves in, say, a splitting field for that algebraic group. So it seemed to be building up evidence that this might indeed be true. The other interesting thing that Alex and I proved about these rational functions is that they have a functional equation in these kind of restricted examples. So there's a kind of symmetry in the polynomials that's coming up as well, which also turned out to be a more general phenomenon, which Christopher Voll has extended greatly in his work, a student of mine in Bielefeld. But actually, the subject took a new turn when I started to do more work with Fritz Grunewald. So I used to go over to the Max Planck Institute, and we would work together there. And actually, we started to analyze these p-adic integrals. And we realized that there was a strategy to calculate these things. And actually, you see, one of the tools that was used by Grunewald, Siegel, and Smith was a little bit of a black box. It was a piece of model theory which was a kind of elimination of quantifiers which didn't give you much hold on what the rational function looked like. So we wanted a more explicit pathway through proving this rationality, which would give you a bit more control on what these rational functions would look like. And what we understood is actually every nilpotent group has a system of varieties which arise from looking at these integrals and doing essentially resolution of singularities on this thing. You can simplify the thing enough such it breaks down into finitely many pieces which can be evaluated in quite a uniform way. But the finite division into these pieces actually depends on a finite division of subvarieties. And for each prime p, the division depends on the number of points mod p in those varieties. So suddenly we saw a very different character coming out of these zeta functions. They weren't looking like zeta functions of number fields. They were now actually looking like zeta functions counting points on varieties. So actually, if you want to calculate a nilpotent zeta function of a nilpotent group, you analyze its presentation. That gives rise to a system of equations. You have to resolve the singularities of those equations, which gives rise then to a system of varieties. You have to count the points mod p on those varieties, and each of those, when you're on a particular configuration, will give you a uniform zeta function. But each of the configurations will depend on the behavior of these varieties mod p. Now, this didn't... this kind of hinted that maybe we should be pushing in a different direction, but what the nature of these varieties was for a nilpotent group was still unclear. It could be possible that they were all just very straightforward, uniform kind of behaved varieties.
Are they smooth projective?
Sorry again?
Are they smooth projective varieties?
Yes, they will be, but exactly after the resolution of singularities, they'll be. But then, sort of, what sort of varieties? Are you just getting affine varieties, or are you getting something interesting coming out of here? So this was a challenge to see what you could get, so I managed to build up a nilpotent group which is class 2. So you've got sort of 2 abelian pieces. The top piece is generated by A1, A2, A3, B1, B2, B3. So the abelianization is 6 generator. And then it commutates down into the center, X, Y, Z, using this particular presentation. So the A's individually commute, the B's commute, but how the A's and B's interact take you down into the center according to this little presentation here. And if you try and look at the subgroups inside this nilpotent group, then what you find is that the subgroup structure actually depends on the number of points over this elliptic curve y squared equals x cubed minus x. And so when you do the an analysis of this, the resolution of singularities will pop out this particular elliptic curve, and then there are two uniform rational functions such that the zeta function of this nilpotent group is expressed as something uniform plus the number of points mod p of this elliptic curve times something else uniform. So this elliptic curve here, y squared equals x cubed minus x, why is that hiding inside this presentation? Well, if you take this presentation, I put it rather provocatively as a kind of 3 by 3 matrix with obviously these two commutators are 0. If you take the determinant of this matrix, you get the projective version of the elliptic curve. And the point is that this presentation, how do you count subgroups? Well, you take two potential abelian subgroups in each of the two layers, and you want to know, well, if I commutate with the generators, is this going to sit inside the potential abelian piece in the bottom? And that's given by certain maps, which will have this kind of the rank of those maps will depend on the rank of this matrix. So if there are actually solutions, you will get to this to actually collapsing the rank of this matrix, that will give rise to more potential subgroups. So the nature of this commutator is absolutely capturing, well, when can I actually have more subgroups or less subgroups? And so this elliptic curve is determining which kind of combinations of abelian subgroups in each of the layers will actually be a subgroup or an ideal. There's still a question, what about this elliptic curve? It might be uniform, its number of points, or might have finitely many polynomials. But if you go back to a result of Hecker, actually the number of points on this elliptic curve is given by, well, it's p plus 1, but then you've got this the eigenvalues of Frobenius giving you the number of points. And if you distribute these, if you look at these as complex numbers, divide by their size, which is Riemann's hypothesis on these things, is a half, p to the half. Then these all sit on the circle here, and a result, an early result of Hecker says if an elliptic curve has complex multiplication, then these are sitting densely as a set of points for each prime p. If you take all the primes p, they'll sit densely. So there's no way there can be, if there were finitely many polynomials, for example, that would still make the thing uniform. Perhaps there are finitely many polynomials which you divide the p up into different groups and it gives you the number of points on the elliptic curve. But if that was true, it would force this not to be a dense set, so they would actually be isolated at certain points. So Hecker's result shows why there isn't a set of polynomials. And if now the Sautoy Tate conjectures are actually proved, so we actually know this is true for general elliptic curves. And you can embed any elliptic curve in a nilpotent group in this way. It's quite easy to write a determinant to write a matrix whose determinant will give you an elliptic curve. So I just chose the elliptic curve that Gauss analyzed because it's a rather nice one. So it gives a result then that the nilpotent group given by this presentation is not finitely uniform. So it sort of took the subject off in a completely different direction in a way, realizing that there's quite an interesting correspondence between the arithmetic geometry that each nilpotent group will have a sort of an algebraic geometric sort of structure associated with it given by this zeta function, which gives you a chance actually to start thinking about some sort of classification of nilpotent groups in terms of the variety structure that these zeta functions give rise to. Actually, when I was doing my doctorate in Oxford, I remember talking to a friend of mine who was doing a doctorate in English literature, and she kept on trying to find out what on earth it was I was doing. And I kept on trying to explain, well, I'm trying to classify things, and I explained the classification of finite simple groups, and that this new tool was trying to help give new invariants to classify things, and she was like, she really didn't seem to be getting it until one day she came up to me in the library in Oxford and slammed down a book and said, I think this is what you're doing. And she showed me this quote. It was actually in an article by Roland Barthes, I think. But it's actually a quote from Borges's, some of Borges's work, who I subsequently have fallen very much in love with. I think Borges is a real mathematician's writer. But in one essay, he had a description of animals, how they were divided up, a classification of animals. So this is a fictitious Chinese encyclopedia that he created for this story, and I thought it was beautiful. You know, animals in this classification are divided into A, belonging to the emperor; B, embalmed; bold, C, tame, all the way down to M, having just broken the water pitcher, N, that from a long way off look like flies. And so I thought this perfectly captured actually a bit what the classification of finite simple groups looks like. It's about as mad as this, with certain et ceteras at certain points. So I actually put this at the beginning of my DPhil thesis as the quotes that began the whole journey. And I think it does rather nicely sort of sum up what a lot of group theory is about. It's trying to just find out what sort of things can happen. And so the nilpotent groups are still a long way from understanding really the complexity of what can happen in a nilpotent group. Seems so simple. Class 2 nilpotent group is just 2 abelian pieces put together, yet seems to give rise to really interesting arithmetic geometry. But there's another question which comes out of that challenge of the atlas of finite simple groups, which is, okay, well, those are the atoms. What are the molecules you can build? So what I discovered is that the work that I have been doing was actually quite helpful for trying to understand, just say the very simplest of the simple groups, a finite group of order, cyclic group of order P. And then you ask, well, what sort of groups can you make out of finite cyclic group of order P? Okay, there's only one of order P. What about P squared? Put 2 together. Well, there are 2 there. What about P cubed? Well, then you've got 5 different ways to put them together. So actually one attempt to, P groups are a little bit like the finite version of nilpotent groups. They are rather wild and messy. It doesn't seem to be anything to get hold of these P groups as you build them up. But there has been a project to at least rescue finite P groups from the categories frenzied and enumerable, because these are generally what most group theorists felt, that P groups just fall into the group. They're frenzied, they're wild, hard to classify, and they're enumerable. Well, maybe they're not. Maybe they are frenzied, but maybe they are enumerable. Maybe there's a way to count these things. I've already told you how many there are of P, P squared, P cubed. Well, what about P to the 4, P to the 5, P to the N? Maybe we can actually count them. And so this is a project which started 50 years ago, or more maybe. Graham Hickman in particular. This is a portrait of Graham Hickman that we have up in our maths department. It used to be in the room that we used to do our DPhil vivas. So you were always examined by 2 people and plus a third at the back. And this was the most terrifying. There's an enormous great portrait of Graham Hickman sitting at the back glaring at you whilst you're having your viva. But it started a journey to try and see, well, maybe we can understand finite P groups by counting them. So if you take P to the P cubed, then there are 5. P to the 4, we start to get some exceptional examples. There are 15 in general, but 14 only if P equals 2. The really interesting thing starts at P to the 5, because now it isn't a fixed number across all primes. We now have a linear polynomial describing the number of groups of order P to the 5. And the coefficients of this linear polynomial depend on P modulo 12. So there are finitely many polynomials. What about P to the 6? Well, this turned out to be a quadratic polynomial. Actually, this is way after Graham had made this conjecture, which is, I'll tell you in a moment. But here you see it's given by a quadratic polynomial, again, whose coefficients depend on P modulo 60. So Hickman wondered whether this might be a general phenomenon, that if you take the groups of order P to the N and you fix N and you vary P, maybe they're given by polynomials in P, perhaps depending on P modulo some value. So this is Hickman's port conjecture, which says that the number of P groups of order P to the N for a fixed N is given by a finite system of polynomials, and you choose the polynomial depending just on P modulo some fixed number N. And Hickman proved this for a small class of class 2 exponent P groups. But the question was there for some time whether this would be a phenomenon that would occur as you built up more and more primes, or could something interesting happen somewhere along the line where these polynomials suddenly disappear. Well, this is actually very much related to the zeta functions that I've been looking at, because all finite P groups occur as finite images of a free nilpotent group of class C on D generators. So actually, if you want to look at the finite P groups, you could take an infinite group and look at the finite quotients of that group and count them up to isomorphism. So that was these zeta functions turned out to be quite a powerful tool to start exploring the nature of these counting functions, counting p groups. So yeah, if you take so let's define p groups of order p to the n. That was what Higman defined. But now let's restrict them to of class C on D generators. All of these finite p groups will be finite images of the free nilpotent group of class C on D generators. And you will have to count up to isomorphism. So this is the action of the automorphism group on this thing. So actually you can define a zeta function encoding these and ask, well, what's the behavior of this zeta function? It's going to be related to the zeta functions of those free nilpotent groups. And indeed, if you take abelian groups, well, we have a classification of finite abelian groups, and you can use that to show that this zeta function can be built out of local Riemann zeta functions. But using the tools that we've developed already to understand these zeta functions associated in nilpotent groups, you can extend those into actually looking at the action of the automorphism group, looking at the thing up to isomorphism, and prove that these two are actually rational functions in p to the minus s. So this is interesting because it gives, maybe they're less frenzied p groups when you count them. This says that if you fix n and if you fix p and you vary n, so these numbers satisfy a recurrence relation. So please note that they are of class C on D generators. We know that the number of p groups grows super polynomially, but if you fix the class and the number of generators, it grows polynomially, and those will satisfy a recurrence relation. So it actually gives some sort of control on the way these things are growing. Perhaps not as wild as we thought. But Higman's port conjecture, of course, is not about the variation when you fix p and vary n, but when you fix n and vary p. Well, that's exactly the question about how these zeta functions vary as you vary the prime p. So the interesting thing is, well, these rational functions, how do they vary then as you vary the prime p? So you can prove the same sort of result as we did with Fritz. You can analyze these integrals and prove a similar result, that there will, for every n, there will be a system of varieties which comes out of the nilpotent group and its automorphism group, and this system of varieties will be controlling the number of p groups of order p to the n as you vary p. So again, the question is, okay, what are the nature of these varieties? Higman's port conjecture says they're going to be very simple. You want varieties that, when you take the mod p, only give rise to polynomials in p. You don't want to see those elliptic curves occurring, because elliptic curves will have a non-port behavior here. So this raises a question, for free nilpotent groups, what sort of varieties actually are you seeing? And how do they vary as you vary the prime p? This was interesting then when one took the group that I developed using this elliptic curve. That was an infinite finitely generated nilpotent group of class 2. Interestingly, Mike Vaughan Lee in Oxford sort of contacted me when he saw this group and said, well, maybe this would be a very interesting group to investigate in connection with the port conjecture. Now, the weird thing is, of course, Mike and I have both been in Oxford for many years. I've talked about this in seminars in Oxford. I published this work in publications IHES and Kreller and Israel Journal about this elliptic curve example. Mike didn't seem to notice any of this. The only reason he actually found out about this group and this work was because I wrote a popular book about symmetry and group theory and the finite classification, meant for completely a non-mathematical audience. And Mike read this book, and at some point I talk about the creation of this particular example. And I put said, yes, if I had one thing on my grave, I would like engraved the presentation of this elliptic curve example or something. And somebody told me that would be very expensive for my family because it's per character. So actually, I remember with Fritz, we went round the graveyard in Göttingen, and there you see all of these equations on the gravestones. I think that's what gave me the idea. But the weird thing is that, so I think actually the presentation is even on the cover of the book. So but this is where Mike saw this thing. So it's actually kind of justified to me. As many of you know, I've spent a lot of my recent years trying to encourage people about the excitement of mathematics, and I wrote this book as part of that journey. But it turned out that it actually helped a piece of research, because Mike read about this group inside this book, not inside a paper in the Israel Journal. And he said, I think this would be a really interesting group. And so we started looking at the question. So we took this group and we made it a group of order p to the 9. It's a 9-generator group, so we just took it out of exponent p. So it's 2 layers of and a sort of fp to the 6 piece on the top and an fp3 bit on the bottom with the same commutator structure. So we had this group of order p to the 9. And so the question was, okay, the way you do this kind of classification of p groups when you go from p to the 6 to p to the 7 is you say, well, every p to the 7 group is built out of a p to the 6 group with a little piece, an extra piece on the bottom. And you count the number of ways you can put another little piece, sort of class 3 on the bottom, and you build up the p to the 7 groups by this p generation algorithm by taking the ones of order p to the 6 and seeing how many descendants that has. So we were interested, okay, what about this group, this p to the 9 group? How many descendants does this have? How many ways are there to extend that to a group of order p to the 10? Maybe that will depend on the elliptic curve that's hiding inside there. So it turned out that it actually did. So the way you have to do this is you take your p to the 9 group and you put this kind of the sort of covering group on top of it. So you have underneath this group there'll be a group, an abelian group of order dimension 14, and then you look at the so you can do all of the extensions to the p to the 10 inside here, and then you have to work out how many are actually isomorphic. This depends on the automorphism group acting on this thing. And it turned out the automorphism group of this group of order p to the 9 actually has extra automorphisms if there are points on this variety. And those extra automorphisms actually give rise to different variations of the number of groups of order p to the 10, which are descendants of this group of order p to the 9. So there's quite a lot of uniformity. It's this point here, when you take primes which are congruent to 1 mod 12, then you have to count points on the elliptic curve y squared equals x cubed minus x, but it was slightly more complicated because they also had to satisfy this quartic polynomial. But we got a difference according to whether, yes, which one is non-zero. Yeah, that's a good point. One of those has got to be non-zero. Yeah, so it's the last one which is non-zero, exactly. So either the number of points will be 0, or if the number of points is 0, then you get this number. But if they're non-zero, sorry, little error there, then you get this number here. So you see that there's a dependence on this variety is causing a different number of descendant subgroups. Again, this cannot be written as that the number of points on this variety that are larger than 0 cannot be written in terms of a Pork function. It doesn't decompose into residues. And so this implies that the number of descendants of this group of order p to the 9, of order p to the 10 of exponent p, in this particular case, is not given by a Pork function. And you can remove the exponent p as well. So this was very striking, because it seemed to imply that maybe this is the point where Higmann's Pork conjecture actually becomes false. That actually at p to the 9 you start to see interesting varieties appearing. This is the way you divide up your groups, p to the 9 groups, and you look at their descendants. And if we're starting to see non-Pork things appearing, maybe this is some indication that Higmann's conjecture is false. But of course, this is just one point in this tree, and the descendants are non-Pork. It's quite possible that if you take all of the groups of order p to the 9, that this behavior can cancel itself out. But we were pretty optimistic when we wrote this paper, which is in the Journal of Algebra, that this would stay like this. But actually, I got a student, Sunjae Lee, who's a Korean student of mine at the moment, and I said, okay, maybe you can squeeze something out which is a bit smaller. What about taking a p to the 8 group? Because there was a way to sort of collapse that presentation a little bit to make it maybe dimension 8. And I sort of challenged him, could he get a p to the 8 example, which has the same sort of non-port behavior of p to the 9? Because that, the interesting thing is that Mike and Eamon and various people who are working on p groups, they've, I showed you this group of order p to the 6. They've now got a polynomial of order for the groups of order p to the 7, which is a polynomial of degree 5, counting the number of groups of order p to the 7. Mike has now gone through the groups of order p to the 8. So Sunjae Lee, this student of mine, actually came up with an example of a p to the 8 group whose descendants were non-pork. But then Mike has subsequently looked at all of the descendants of groups of order p to the 8 and understood that there is a cancellation. You can actually choose these p groups such that the descendant structure looks quite exotic, but it's somehow the way you're choosing that particular direction that causes that interesting behavior. So now we're much more skeptical whether this particular example that we produced is an indication whether Hickman's conjecture will be false. It's very interesting that you're getting this non-pork behavior as the number of descendants coming from these extra automorphisms, but whether this will be just cancelled out is still very much an open question, which I think is always an exciting state to be in. So thank you.